All right, just to help out with logarithmic differentiation, I want to show one more example. Logarithmic differentiation is useful when you have some function of the format like the previous one, like x to the power x. Anything where you have a function raised to a power another function, you can equals y. You can use logarithmic differentiation to help you with that. Okay, and it'll work out pretty similar to the last one. But another situation in which logarithmic differentiation is useful is when you just have like a complicated, messy-looking rational function, like this one. We could apply the quotient rule to this. That would be fine. Actually, it's not super hard to apply the quotient rule, but I just want to kind of demonstrate the alternative approach. The alternative approach is going to use some more exponent rules. So remember that if you have the log of like a times b, you can separate that out as log of a plus log of b. And if you have log of a divided by b, that's log of a minus log of b. So those two logarithm rules, along with the one I mentioned before, where you can pull the power out like that, those rules can help us simplify things down. So what we do is we take the logarithm of both sides. And by the way, I pretty much always use the natural logarithm because its derivative is the easiest to work with. But technically you could use any logarithm you want here because they all follow these rules. Okay, so we take the log of both sides, and then on the right side, this simplifies down. So we can use that subtraction thing, so we can do the log of x plus 5 cubed minus the log of 6x to the 5th. And then you can pull the 3 out here, 3 times log of x plus 5. And then this one, we can be split up into log of 6 plus, and then pulling the 5 out, 5 times log of x. And this negative should get distributed across here. So we end up with log of y equals 3 log x plus 5 minus log 6, and then minus 5 log x. And so now that we've done that, now we can do our implicit differentiation. Let's take the derivative of both sides with respect to x. So we get 1 over y times the derivative of y on the left, just like we did in the last video. Every time you're doing logarithmic differentiation, or often at least, you get this on the left. If you just started with y, you will end up with this. But on the right side, now we do the log of the derivatives of each of these terms. And the idea is that these derivatives individually are easier than doing the quotient rule. So I don't know how much you agree with that, but let's see what we get. So we got a 3. Derivative of this natural log is 1 over its input, x plus 5. And then chain rule says multiply by the derivative of x plus 5, but that's actually just 1. So there we go. Then do the derivative of the natural log of 6. You don't need to apply that log differentiation rule because that's just a constant, so actually its derivative is 0. And then we'll have the derivative of this third term here, which is still going to have the 5 constant multiple, times the derivative of x, natural log of x, which is 1 over x, like that. So we have this. I forgot to put that parenthesis there. So we have 3 terms. There we go. So now dy over dx is going to be this stuff, 3 over x plus 5 minus 0 minus 5 over x. And then what you do is you take that entire thing and you multiply by y so that it cancels out on the left side and you get y on the right side. So you could put y here, and if you wanted it in terms of both x and y, if you were okay with that, you could leave it like that. Or you can replace the y with what y was equal to when we started, which was the x plus 5 cubed over 6x to the 5th. And then now we have dy over dx as a function of x. So there's another example of logarithmic differentiation.